Hopefully this is a quick video today. I'm taking a look at this little induction heating unit that I got from Aliexpress in the last mailbag. If you haven't seen the mailbag, I'll put a link to it up there. The point of this thing is it'll take a DC voltage in from 5 to 12 volts. Using the circuitry on here, it will pulse that voltage at a very high frequency, send it through this coil, and then if you put a piece of ferrous metal into the middle of that coil, it will cause induced current into the metal, as far as I understand, and it will cause tremendous heating in a very small area. Obviously, there will be heat conducting up through the rest of it, but in a very small area, the area contained within the coil, it should get really hot. Now, knife makers and blacksmiths tend to use these to spot heat their work rather than having a big forge going, and those are much larger units than this one. The coil is often made out of copper pipe, copper tubing, instead of just wire. This looks like about 16 gauge wire, and in those higher powered units, that pipe would have coolant running through it so that the heat radiating back off the workpiece doesn't melt the coil. But this is smaller and presumably won't generate quite as much heat. It runs at between 5 and 12 volts input, and according to the listing, it is supposed to take up to, I think, 200 watts? I stand corrected, 120 watts, but still, at 12 volts, that's 10 amps, which when I was experimenting with it on my bench power supply, overloaded the power supply and drew it way down. So that isn't going to work. You need a much beefier power supply. So I am going to test it using a 3S pack of LiPos, which should give very close to 12 volts. I've been charging it for a while, and it's fairly close to fully charged now. Let's just check it. Yeah, okay, that's a full 12 volts. It may not put out current for a super long period of time, but we'll have to see. Not sure how well those salvage cells will be happy pulling 10 amps out of them for how long. Anyway, I did take a little bit of time before I started the camera to reverse engineer this thing, or at least partially. There aren't a lot of components on there. There's a couple of transistors here. They are very beefy MOSFETs. There's a diode and then a smaller diode here, which I'm thinking is probably a Zener, but I can't really tell. I can't get a part number off it. And resistor, a little cluster of those guys. And then hidden way underneath there, there's another cluster of components which appears to be the same thing, although I can't get a probe in there to measure them. And I did try desoldering these coils to get them out of the way, but I was having to throw a lot of heat into there, and I didn't really want to destroy this before I experimented with it. But let me show you, before we carry on here, the rough schematic that I came up with. I drew it across 2 pages just because there's the half that I'm confident on, this part, and the half that I'm much less confident on because everything is buried and I can't follow the traces very well because black on black and everything's pretty well hidden. And with the low resistance coming from the coils, it's really hard to ohm it out without, again, disassembling it, and I really didn't want to do that. So the part that I'm confident on, there is the output coil. It has in parallel with it those 2 big capacitors on the back of the board. These guys here, they're 0.3 microfarad. In parallel with those 2 is the 2 coils in series, those 2 big inductors you see on there. They are in series, and their joining point goes to the positive voltage input. I don't think there's anything else connected there under there, but again, I couldn't see it. Then we have the 2 MOSFETs over here. They are D484s, both identical. Both have their drain connected out to this operation out here. Both have their source going to the negative voltage input, and their gates go off to that other collection of components. These little guys here, and presumably their partners underneath there. And as far as I can tell, asterisks all over the place, disclaimers, disclaimers, etc. This is approximately what it looks like. The larger diode going up to the positive voltage, and this is the one that's hidden underneath the coils, and I couldn't tell. I think that's the way it goes, but I can't tell. It would make sense if it went the other way. I don't know. Just pretend this is a bit of a mystery, similar to this, but not exactly the same. There's that larger 470 ohm resistor. That's this one up here, and its partner there in the other half of the circuit. This one goes to the visible ones. This one goes and disappears underneath there, presumably to the other ones. Then there's this MELF diode here, and again, another one hiding underneath there. Based on the band on it, that's how it's connected. Maybe it's a Zener, maybe it's something else, I don't know. And then hidden in underneath there as well, there is a really small 10K resistor, which presumably is pulling the gate to ground. There's the gate of one of the MOSFETs, and there's the gate of the other one. But enough about the theory, such as it is. Let's just grab that and connect him up to here and get this show on the road. That is a resin print, so it shouldn't melt. Yes, it's a giant wing nut. I was just messing around. That shouldn't melt, and that'll just hold that up off the bench. Let me get everything prepared here. I would like to see what current this thing is drawing. So we'll use my Unity UT210E, which is an AC and DC clamp meter. You know, somebody complained about that in a previous video. This can do DC clamping as well. Oh, that makes it hover. Okay, there's that. I've got a thermal camera just over here to experiment with. So let's, I'll get everything set up and let's try this. So with the battery connected, we got an LED on there. We're drawing about 1.8 amps just with this thing sitting idling. And the thermal camera, while it can see that warming up, it's below the threshold. I've got this set to 100 Celsius plus because I'm assuming if this works, it's probably going to draw a lot, or heat this up a lot more than that. So let's put this guy in here, and immediately we're drawing 4.6, 4.7 amps. So that's good. That tells me that something's going on. And the thermal camera is showing the hot spot is now 145 and rising. So that is the nail. We'll just put that in the middle so we can see it better. Yeah, 140. So, oh, and the nail's starting to discolor. Cool. Let's put it back in there and just see what happens. We're drawing pretty much fully 5 amps down here now. Wish you could see that without the glare. And we'll just let this go. We're up to about 180 or so on the nail, according to the thermal camera. Trying to hold it steady in there. I don't know whether that's the move or not. We're up to 225. I wonder how hot this thing's going to get. I should have a voltmeter on here too, just to keep track of it, but I don't. I wonder if I can optimize my heating by watching the current. It's drawing currently 4.5 amps basically. What do we got here? We are up to 375. Oh wow. Does that mean, oh yeah, easily. Okay. It's not forging temperature. Not sure what that is because I'm not a blacksmith, but let's just see what we can get out of this, I guess. I don't know what the end game of this video is, but I do know that that nail is quite hot. And I can see the temperature discoloration moving slowly further out here. What are we up to? 350, 347, 370. So I've just reset the thermal camera to more normal temperature ranges, and what are we getting here? Oh, that coil is over temperature. Okay. Ooh. And that output connector is also over temperature. That's, oops. Okay, I've just put this back into the high temperature mode. 120 degrees is the cutoff between the high temperature mode and the low temperature mode. So the coil right now is sitting at about 175, which is pretty hot. This connector down here is sitting at about 140 or so. And for these cheap plastic connectors, that's probably not ideal. But I don't think anything else is over 120 on there, so I guess we can live with that. But I think I do want to unplug this now and just let everything cool down, because it's not ideal that that connector there is getting so hot. And I don't suppose it's really good for that coil to be hovering around 160 degrees either. Yeah, let's let that cool down for a little while here. Just for fun, let's see what this battery pack looks like. They drew it down a little over half a volt. That's to be expected, I guess. And it is warm. I'd call that maybe 30 Celsius or thereabouts. Not ideal for those batteries. And how long were we running that for? 5 to 10 minutes. I don't know. I wasn't paying attention. But again, we could double up that pack if we wanted to do it, or use a heftier power supply, I suppose. But just for salvage cells, yes, I always use salvage cells. That didn't work too bad. But there is one other experiment that I want to do once this thing cools down a little bit. I want to clamp my scope on across there, and I'll probably just run it briefly and capture it as a still on the scope, and then we'll go over there and take a look at that just quickly. So there's a freeze of the pulses. It pulses it and then it rings for a while. That's actually the second ring of that one. I didn't quite freeze it in the right spot, but it pulses it and then it rings down for a while. And what is the amplitude of the pulse? Looks like it's about almost 2 volts amplitude, peak to peak of the pulse. I'll just get my cursors into time mode here. So if I got my cursors in the right spot, it looks like it's pulsing it at just shy of 200 kilohertz. I don't know how informative that is, but it's definitely a high frequency device, so that's another data point, I guess. I'm a little disappointed in myself that I couldn't do a proper reverse analysis, reverse engineering of this, but again, I wanted to actually be able to use it, so I didn't spend as much effort as I could have disassembling it at the risk of not being able to reassemble it. I said these big copper traces here act as a pretty significant heat sink. You can see that I tried to get in there and desolder it, but it wasn't having it. I suppose if I could keep that nail as hot as it was, I could dump a lot of heat in there quickly, but no. Anyway, fairly simple little device. It does what it says. And again, you don't want to run it for huge amounts of time because it does get really, really hot. And I expect it would deform this connector after not too many usage cycles. Like I mentioned, the larger, higher current, higher power commercial units, I mean, everything's bigger, the voltage is bigger, the current's bigger, and this is made out of tubing with cooling running in it to eliminate the risk of everything melting down. But anyway, that's what I wanted to know about the thing for now. One thing I may use this for is if I've got some stuck bolts and things like that. I've seen mechanics using this to get down over the bolt onto the nut, just apply heat, which with a stuck mechanical fastener, the heating will create some expansion and then the cooling contraction, which usually breaks the corrosion enough that you can get a wrench on it and actually pull it apart. I don't do a lot of that, but occasionally when you get something that's super stuck, maybe this will be the answer. That's enough. I said it was going to be a short video. It's a short video. Thanks for watching. Questions and comments down below. I'll talk to you later. And before anyone asks, the beer was Diabolically Decadent Brown Ale from Dastardly Villain Brewing in Winnipeg. I've had this one before. It's a good one.